lists and futures and completable futures, and you can write code which will work with any of those, which I think is going to become relevant in most mainstream programming languages over the next few years, because we're increasingly writing more asynchronous things and having more complex things enter the JDK, like the computable future. And then I'm going to end up on trying to defend implicits. So who here has used the Scala programming language on a non-toy project? Who here likes implicits out of that group? A few? There you go. Well, I think that implicits get a bad name. I think they're the feature which, if you were to ask your colleague and you say, hey, I'm going to start using Scala as a programming language, they say, no, we don't like it because of implicits. So I'm going to do a little defense. I'm also going to show some really bad uses of implicits, ones which we certainly don't do in the code bases I work on, but have given them a bad name. So, programming languages. Which programming languages do people work on? I think this is a small enough group that you can just shout out, and if you want to ask questions at any point or anything's unclear, just raise a hand or shout at me. So, who is using Java as their primary programming language? Mainly Scala, Kotlin. Is any of the people who are using Java thinking about using an alternative JVM language like Clojure or Scala or Kotlin? A few? Cool. Well, I think learning programming languages is fun, and I think the industry we work in is great that we can, all you need is a computer that's probably within 10 years old, and you can go and learn new tools, new techniques, etc. We're not building roads or bridges, etc., where we need to experiment with slightly more dangerous things. And I think the more programming languages you learn, the easier it becomes to pick up new programming languages, and you see the common features between them. And I think if you flip between a language, I've worked quite a bit in C#, I've worked quite a bit in Java, Golang, and Scala, and like flipping between Java and C# is almost trivial from a language point of view. You have to learn a new IDE, which is a bit of a pain, and the ecosystem and the CLR is very different to the JVM, but it is the same paradigm, which makes it very easy to learn, and the libraries are very much inspired by each other. One of the hardest parts of learning Scala is it is its own paradigm. You may have done Haskell, you may have done Java and C#, but Scala sits somewhere in the middle and allows you to do both things. It allows you to do very functional things. There's part of the Scala ecosystem which believes and promotes pure FP, which is where your entire program, apart from the thing you run at the end, is referentially transparent. If that term doesn't mean anything, it's one of the ones we'll cover. All the way through to large chunks of Scala code bases I've worked on are just Java, but using pattern matching and case classes. And there's nothing wrong with those either of those two sides of the spectrum, but I think it's important to at least aim for where the language designer, the person who came up with the language's vision of the programming language, and that's of a hybrid between functional and object-oriented programming. And some of the things I'm going to show will use things like currying and partial application and function composition, but we'll also combine that with classes and objects. So, semantics and syntax of a programming language. So, I'm sorry if you already know this, but I just wanted to quickly jump through it because I use these terms quite a lot throughout. So, the semantics of a programming language is its actual behavior. It's what it does, it's what it means. So, whether a control flow structures like ifs and whiles, are they statements or are they expressions? That's something very important to know about a programming language. How does the concurrency model work in that language? These are important things. But one of the nice things about the semantics of a programming language is you could learn the semantics of a programming language in 5 minutes. I don't know Kotlin very well, but I'd really like to. And if we went for a coffee, we could exchange and I could learn the big things about Kotlin. How does concurrency work, just from a high level? How does control flow work, etc. Syntax is just the stuff we type. And it often blurs the image. We often think far too much about syntax. So anyone who's tried a list-based language like Clojure, like, what do you think? Do you try and learn the language, or do you just stare at the parentheses and be confused? And I'm going to show you a lot of square brackets over the next like 30 minutes. So you have to promise that you'll not get too hung up on the fact there's lots and lots of square brackets, and we're just trying to think about the behavior of what's going on. Something which I accidentally do a lot is confuse unfamiliar syntax with complexity. I've been doing Java for about 10 years before I looked at Scala as a programming language, and I initially thought, this is really complex, it's very different. Why does this JSON parsing library? What are these type classing things? And it's really, I think, important that you get in a beginner mindset to learn Scala, because it is a different paradigm. It's got lots of unfamiliar concepts, and it's got lots of unfamiliar syntax. So, audience participation is mandatory. What does this evaluate to in Java? This is not Scala. What would happen if you did this inside Java? Anyone brave enough to shout up? Would the compiler allow this? Any guesses? No, it's not going to compile. And this is the only bit of code throughout the entire presentation that doesn't compile. The thing I use for my slides pulls code from a project and dumps it into HTML, so you can, anything up here is something you can compile and take away. And the reason this doesn't compile is one of the most fundamental things about Java is it is a statement-based language, which means that when we have control flow, the stuff you shove inside the control flow has to do side effects, has to have side effects. Otherwise, there's no point. And correct me if I'm wrong, feel free to shout out. I think the only exception to that is the ternary operator, which is the question mark, colon thingy, and that you can actually assign to a variable. So in Java, you'd have to do something like this. You'd have to do something side effecting inside your control flow structure, otherwise, what was the point of doing it, apart from the fact maybe you get paid per day and per line of code that you write. And if a language is statement-based like this, it normally encourages things to be mutable, because one of the most fundamental things you can do as a side effect is to mutate some value inside memory. So what about this? Does this compile in Java? Any guesses? Who thinks it compiles? Who thinks it doesn't compile? Who doesn't know or doesn't care? There you go. It does compile inside Java. However, if you were to actually use the should act variable, then it would stop compiling. Or at least it did at Java 8 or whichever JVM. Just double check this. And it would say, sorry, should act could perhaps be uninitialized, so you definitely can't use it. You could have this somewhere inside your code as long as you don't use should act. So what does an expression-based language look like? That's the first big thing that's going to hit you, and you might not even notice if you switch from, say, Java or C# to Scala. Well, this does compile in Scala because every bit of the control flow in Scala is an expression. An expression is something which turns into a value. So if I were to have the value x equals 12, then this would evaluate to the first, the true. But if I were to have x equals 5, I could evaluate it to false, which means I can do this. And this seems like a trivial difference, but it suddenly means that by default, virtually everything inside Scala is immutable, because you've got expressions, so you can always just assign things to values rather than having side effects which mutate things. There are many other syntactic differences as well between Java and Scala. For instance, I could write it like this, which you might love or you might hate, but it's just different syntax. Maybe you really like the curly braces, maybe you don't, maybe this is fine for you. So one of the takeaways is if I were to learn a new programming language and you were trying to sell a programming language to me, the first question I think that is worth asking is it statement-based or is it expression-based? And statements have side effects, but expressions evaluate to values. So that really allows us to promote immutability in a language. And I think once you spend a lot of time in a language where things are immutable by default, I find it hard to go back. So another term which I use a bit is referential transparency throughout this talk. So if we've got a value that's x, and this does compile in Scala, because Scala has this value in scope all of the time called question mark, question mark, question mark, which is the bottom of the type system, so you can assign it to anything and it will just massage itself in there. So this does, but if you were to run this code, it would say, why are you using this? And it would blow up and say, don't do it. So, referential transparency means that we can substitute anything on here with the right-hand side, and we'd end up with the same program. So, if I didn't use the question marks, and I said x was equal to 4, this would be referentially transparent, because whether I put x there or whether I put 2 4s there, we'd end up with the same program. Would this be referentially transparent? Any guesses? Yes? No? No? Someone thinks no. And it's right, because if we substituted the right-hand side of x into here, we'd end up with a different program because it would print things twice, assuming that we cared that things were printed to the console. And printing maybe is not too important, maybe you can get away with that, but suddenly, when you've got a language which allows this, and Scala does, and obviously Java does, it means that, imagine you were talking to a database in the value x, or imagine you were calling out to an external service. Suddenly your program would be very different if you started substituting things. Anyway, so we've covered referential transparency, we've covered semantics and syntax. Now on to the first actual proper part of the talk, which is to promote and use function composition. So function composition allows us to take two functions and produce a new function from them as long as the types line up. And I'm hopefully going to promote and convince you that function composition as a way of structuring your application has some really amazing benefits. It completely decouples parts of your application. It allows the functions to be tested completely separately, but I'll leave it up to you. And if functions can be pure, and by pure I mean they're referentially transparent, and they're even better because they're easier to test and you can substitute them. You can do that inline refactor inside IntelliJ or Eclipse, and it will never change your program. As soon as something isn't referentially transparent, then every time you use that very easy inline function, you might not be producing the same program. But I'm not going to go from a purist functional point of view. We're happily going to use function composition with methods that are on classes. So if there's any Haskellers in the audience, you're probably starting to cringe, but we're going to do that as well. I'm going to show how, if I was building a web app, how I would structure the code for that. So we're going to start off with a type alias, a feature which Java doesn't have. So the syntax on the right is a way to represent the type of a function inside Scala that takes one parameter. The only difference between that and Java is Java would probably be a single arrow rather than the equals in front of the arrow. So we could say that a web request is a function from HTTP request to HTTP response. And even if you're using JAX RS or Spring or servlets directly, that would be a method on a servlet or a controller, etc. But each of those individual HTTP requests, they would be a function from HTTP request to HTTP response. Type aliases are one of those little features that Scala has that I really enjoy because we can give names to things rather than having really long type signatures, which can become cumbersome. These are case classes. So case classes are a syntactic thing inside Scala. They're not adding any new semantics to the language, they're not adding any new functionality. It's the equivalent, if in Java, is if you had an object which had some final fields and you override hashcode and equals, something you probably get IntelliJ or Eclipse to do for you a lot. Or if you use something like Lombok or immutables and it generates those kind of data classes for you. This is the one bit of syntax which I think a language like Scala and F# have that really do make a fundamental difference though, because once you can define your data classes on one line, or your value objects as some people call them on one line, it does enable you to put your entire domain on a single page that you can discuss with developers, which is a feature I love of programming languages. So I don't have to navigate between files to see like all of the domain objects that I've got. Anyway, these are just some data classes. Now I'm assuming maybe we're using some framework for this or annotations, etc. But at some point, if we're doing a HTTP request, we're going to have to do some serialization and deserialization. Maybe that could be JSON, it could be protobuf, it could be something. I'm just going to hide it behind this interface. And it's got the word trait, which is something Scala has, but we're just going to imagine that to be the same as an interface for the purpose of these examples. And we can serialize from a customer into a HTTP response, or we can deserialize from a HTTP request into a person. What else do we do? So I'm going to assume that we're going to start off with a layered approach. So we have our controller or resource or whatever we want to call it, depending on which framework or terminology we like. But it's the bit that knows about the web library that you're doing. And it's normally a good practice to keep this separate from your core business logic that probably only knows about the stuff in your programming language and your domain. So what does a controller do? Well, it deserializes it, assuming that it's not done by some annotation-based framework, and then it calls into some service, and I'm expecting that to be the code where your business logic is. We get a response back, and then we serialize that and send it back. And what this is doing is it's turning people into customers, hopefully, which is what we're all trying to do at some point. But I'm not worried about what the logic is behind that, just the way we structure our application. We've got dependency injection, so we're taking in our dependencies, so the controller depends on the service, the controller also depends on the serializer. This is the Scala syntax for defining a constructor and having final fields and assigning to them, so you don't have to duplicate it like in Java. What else? Yeah, so that's just the web control. What do we do inside our fancy, awesome business value? Well, nothing really, because I don't want to write a fake fictitious application. We're trying to talk about Scala. So here what we've got is we've got another dependency, because often as part of our logic we decide, hey, we want to persist something. Maybe that's a repository or a DAO or something, but the application service is going to depend on that. And I don't really do anything. All I do is instantiate it and save it. But what we're going to do is convert this to stop using direct dependencies. So we don't want our application logic to know about the data store. We don't want our controllers to know about our application service. We're actually going to pull this out and treat them as just functions and then use function composition to stick them together. And I think this has some benefit, because an argument I've had for years, or a discussion, shall we say, that we repeatedly have, is should we do mock-based testing? And the question is, let's say I'm testing this application service. Who here, and you have to answer this time, because I'm going to ask both questions, both who wouldn't and who would, who here would use a mocking library for a customer repo and validate that you've actually saved the customer? Who would do it? Who would do that? No one? You tell us, quite a few. Who would not do that and thinks mocking libraries are the worst thing that were ever invented? I'm sure there's a middle ground there. But it's just one of those discussions that you have in software development. We have them over and over again. And if I was writing a layered application like this, I would probably go with yes, I'm going to use the mocking library, and I'm going to mock between the abstraction layers. The abstraction layers being I've got Webby controlly, I've got business logic, and I've got kind of infrastructure repository stuff. And I'll just make sure that we save the customer, and I'll do that potentially by a mocking library. So the repository is just another interface. We don't need to worry too much about that, but it persists things to a database. And I'd say this is do-it-yourself wiring. Well, it's one way. We're doing two types of wiring here. We're doing dependency injection, which is often okay because we've got quite a few cool frameworks on the JVM to do the dependency injection for us, whether we want field-based or constructor-based injection, that's fine. But we've also done our wiring between layers. We've explicitly had to write code which says that once we do our business logic, we then save it off to a database, and that's why you suddenly feel like, yeah, maybe I do need to test that. And instead, I want to show an alternative. So we're going to use three language features to avoid this, and the three are function, composition, currying, and partial application. So let's see how we do that. So I'm going to start with using adding and multiplying as an example to describe these three terms, and then we'll go back and show how they're useful for a real-life application. So I'm flipping back to Java for a second. So imagine you have a function that is add, because you really dislike writing the plus operator because you maybe have to press shift. I don't know. Anyway, you want your own add function which takes two integers and adds them up. It's very common in programming to take a generic function which takes multiple parameters and specialize it down to something more specific, like add 10. Hopefully that's not too exciting. And in Java, you'd have to explicitly write that function and delegate to the other function hardcode one of the parameters. We could do the same, and we could add our own multiply function because we're getting excited about math. And we can specialize that one again. And then what we can do is we can then compose those two functions to create some really exciting logic that adds 10 and then multiplies by 10. Right? And this is function composition. Up here, this is partial application. Maybe it would be the other way around though. What we've done is we've taken a function which takes more than one parameter, and then we've turned it into a function that takes fewer parameters by basically fixing one of the parameters, or two of the parameters, or three. Same for function composition. What we've done is we've taken two functions and we've taken one input, we've passed it to one, and then we've passed the output of one into the other. Hopefully this isn't too exciting. But this is something we do manually inside a language like Java. And see the same in Scala. So imagine we had the add function, we've got a little syntax, we've got a little bit less few curly braces. We can do exactly the same thing in Scala, obviously. We can have an add 10 as a specialized version of that function. But there's something else you can do inside Scala. You can have a curried function. So what on earth does that mean? Well, it's not about what kind of dinner you like, it's about parameter lists. So curried functions have the parameters as individual, as separated. So you can think of a curried function as it takes one parameter, and then it returns another function which takes one fewer parameters. So in Scala, you can write them all and say you have to pass them all in, but you can also separate out your parameter list and say, it's quite all right if you only want to pass X to me. Now, of course, that's not going to do any adding. it's going to give you back another function which expects another parameter. So what do we think the type of addCurrent10 is? If I were to ask you what the type of this is. Does anyone want to be brave enough to shout out?
Function.
Pardon?
Function.
Function? Wait, which parameters?
Function with an integer and return an integer.
Yeah, exactly. So if we were to actually ask for the type of this inside Scala, we'd end up with a function from integer to integer. And then what we can do as well, because not everyone defines their functions like this in Scala, is we can take any function which wasn't originally written to be curried and just ask for a curried version. So if someone else hadn't written the parameter list separately, you can just say, give me the curried version, and it will break them all out for you. So let's see this without all the options. If we curry both our functions, both add and multiply, so they both take 2 parameters, but we're saying it's okay to just pass in a subset of the parameters, then we can implement add 10 and multiply 10 by saying add 10 compose multiply by 10. And it goes right from left, which can seem weird, but when we wrote it manually in Java, remember, because it's a thing on the right which is executed first inside the Java example too, the add 10 was inside the call to multiply by 10. Scala actually has both. It has the normal right associative function composition, but it also has and then, which is exactly the same thing, but it goes the other way around. So a lot of the time when doing businessy logic to say this happens and this happens and this happens, and then reads far more naturally than compose, because you can say it's add 10 and then multiply. And this works really well for things like data pipelines, like when you're using and composing functions in things like Spark, and we'll see it later for the HTTP request example. So partial application and currying are very, very related concepts. It's easy to get confused between the two. So currying is just the enablement of a language to say that the parameter lists can be separate, so that you can pass in a subset of them. Partial application is when you actually use that and build specialized functions with a subset of the parameters passed in. And then function composition. Function composition is gluing these together. And sometimes we're in this wonderful idealized world where the types line up. So if we have a function from string to integer, and we have a function g from integer to bananas, because I like bananas, and we say g compose f, then what we're going to end up with is a function that goes directly from string to bananas. Alternatively, we can say f and then g, because maybe you want to read that you turn it into an integer with f before you use g to turn it into banana. Right, we're going to move away from integers and bananas and addition, because I can't imagine many people's domain that they're working in right now is the conversion of integers into bananas, but I imagine a few people here are building web services. So this is all just the code we've looked at before in the more traditional layered approach. Just a reminder that our end goal is to get a function from HTTP request to HTTP response, because that's what we love to do. And we're going to try and replace this with using function composition, partial application, and currying. Reminder of what the application service looks like, just so we've got there, and we can kind of think of it as a function from person to customer. So this is our goal. Our goal in life is to produce one function for one HTTP request, and this is how we're going to do it. Well, if we forget about the traits and the interfaces and the classes and the dependency injection, deserializing a person or deserializing whatever thing which comes into your application, we can think of that as a function from HTTP request to person. That's what you inevitably have to write. Maybe there's some JSON blob inside that HTTP request and you need to use a library like JAX and pull it out and do it, but it's kind of what we need to do. If we think about our business logic, even though I haven't written any, would be from turning people into customers. And it might be in a class, it might not be in a class, I'm going to show examples of both, but it comes down to a function from person to customer. Saving a customer could be a function from customer to like unit or void, if it's just saving it and not doing anything to it. Or it might be a function from customer to customer if you're adding some identifier that's generated by the database or something. Maybe it does return it, use auto increment or something. So that could be either. And then finally, we want to send it back over the wire. So non-businessy concern, that's something we need to do. We need to send the response back over HTTP. So if you assume you've written all of these functions rather than them just being question marks, then when you come to do something and actually do something in whatever web framework or web library you're using, the way that you can actually do it is using function composition. So we can say that a register customer web request, which is a function from HTTP request to HTTP response, what it does is it deserializes the person, and then it creates the customer, and then it saves the customer, and then it serializes it. And this will compile because all of the types line up. And for this to compile, the output of one function has to be the input of the other function. I think this reads a lot better than if we were to do a compose, and then with compose we'd have to turn it all around, so you'd be kind of reading your logic in reverse. And yeah, and this type checks, and this is how we construct our application. So the question then is, are we done? Because we haven't used any partial application, we haven't used any currying, and we seem to have completed our business logic all just using function composition. Well, if I flip back to this, how many people save something to a database without a database connection? It's pretty hard, right? You need something, whether you're using JDBC or Cassandra or Kafka or something, there's no way you can write this save customer function unless you've got some global context, some database connection pool, etc. So that's the next problem we need to solve, because it really isn't as simple as saving a customer as a function from customer to customer. And that's where the currying and partial application will come in. So I'm not going to use any particular database or HTTP library or queuing system. I'm just going to assume there is a class, there is an instance of an object which represents something you need to be able to do databasey stuff. And I'm going to call that a database connection, which is very imaginative. Right. So really, a function which saves a customer is a current function whose first parameter is a database connection, and second parameter is the customer that we need to save. This is object inside Scala. I haven't introduced that. So it's just a way of grouping functions. It turns out in the Java language to be the equivalent of like a singleton. But it's just used for, I could have removed that. It's just a way of structuring functions and grouping them together. So this is one way of taking in a database connection. But this would break our function composition, because no one's returning a database connection to us. The step before this was our business logic, which certainly shouldn't know anything about database connections. But because this is a curried function, we can partially apply it. So when we actually structure our application, when you write your main method, or you instantiate your resources, or however your application works, what you do is you create a database connection, and then you can take the save customer function, you do this once, this is like the initialization of your application, and you would partially apply it, give it the database connection, and because we've partially applied it, we're left with a function from customer to customer, which is exactly the type signature we need for the previous thing to compile, where we do and then, and then, and then. So there we go, everything works again now, because we've managed to have our save customer both have a database and be able to fit inside this function composition. Is this the only way to do it? Absolutely not. It's very common to group functions that have similar dependencies inside a class. That's a common thing to do. So we could have a class here, which is the equivalent of a class inside Java. And the constructor could take the database connection, and then the save customer could be a method on the class. And one way of thinking about a class, if you don't have any other states, etc. in there, is a group of functions which all have the first parameter list, which is the constructor. So let's say we had save customer, update customer, lots and lots of different database functions. We could write them all as completely independent functions, and the first parameter list would be the database connection. But another way of thinking about a class is that it's just a set of functions which share a parameter list, which is the constructor. So how does this work? So in the initialization part of our application, we can instantiate the data access class. We can pass in the database connection, which is whatever that is. And then at that point, we can pluck off the methods of the classes. And if we pluck off the save customer method, which we do here, that is the right type. It's certainly not pure functional programming, and anyone, if I said it was, someone could hit me with a stick. But it allows us to structure our applications and the flow between our applications with function composition rather than explicit layering. Is this the only way? Nope, more ways. So another way to do it is with implicits. And we're going to talk about implicits a bit more in the last section of the talk. But this is reasonably common inside the Scala programming language and inside libraries, is that you can make the final parameter list of a current function to be implicit. And what that means is you can, but you do not have to pass in things, pass in the last parameter list. And what the compiler will do is look in scope, anything that you currently, any variables or fields that you currently have access to, and it will try and find one there's a type database connection, and it will pass it in for you. You could pass it in yourself, that's fine too, but the compiler will do it for you. If you can't find one, it won't compile. If it can find two, it won't compile, because it'll be like, which database connection am I meant to pass in? So during the initialization of our application, when we do this, when we pluck off the saved customer, there must be an implicit database connection in scope. And the way you make something implicit is you write implicit in front of it. So we must have instantiated a database connection and explicitly said that this is allowed to be used as an implicit value. And again, this will fail to compile if there isn't one of these in scope. So it's far more explicit than, say, a runtime reflection-based framework looking around for classes with constructors that mapped and instantiating them. So they're pretty explicit implicits. Right, so that's the first section over. So we've used quite a few different techniques. Hopefully you know what they are now. We've used function composition, currying, and partial application as a way to glue together bits of our application, so we're not explicitly calling from the database layer to the web layer to the business layer to the database layer. I've put here that the benefits are reduced need for mocking, and maybe you don't need a DI framework anymore, but I think the main benefit is it really decouples the parts of your application. The only coupling between the layers now is the types have to match up. Never does one layer of your application see a class or has a dependency on another part of your application. Right, higher kind of types. Right, so what is a higher kind of type? So we've got normal types, like string and int and ones that we've already created during this talk, like person and customers, and they are real types. They're types you can instantiate, they're types you can pass around, they're types you can touch and massage if you want to. In Java and in Scala, we also have these like kind of funky types that were added inside Java 1.5. And they're ones with generic parameters. So we've got like a list of t, and it means we can write our code. You could write some functions which accept a list of t, and you could write it so you could pass in a list of strings, or a list of ints, and a list of people, or a list of customers, but you wouldn't be able to know what methods are on there apart from hash-coded equals. And that's become pretty much normal inside the Java programming language to deal with this type of generics. But if you're around in the Java ecosystem when they were first added, that was a lot of new syntax to learn. And if you get onto covariance and contravariance, which is where you have the question mark extends and the question mark super, I still have to look it up, and I still find the syntax quite complicated. One thing that's common in a language like Scala, we can do this, and we can write abstract code for things like lists of t's, etc. But we can also write abstract code for this side, so the list and the iterable. So you can say, I'm going to write some code which works with a future or a list, because they both take one type parameter. One way of thinking about these types is they're not a real type. In Java, they happen to be a real type for backward compatibility. So you can have list as a type in Java, but you'll get a compile warning. It'll say raw type or something. But that's just for backward compatibility. If Java was created from scratch, you wouldn't be able to pass list around. You'd always have to pass a list of a type parameter, or a list of question mark around. What they kind of are is just a function which takes a type, like string or int, and then produces a real type. And if you don't care what the real type is, you can write code which just deals with a list of anything. You can say a list of t or a list of object. And of course you can do this in Java, but what you can't do is you can't write abstract functions which deal with a something of t, like a list of t or an optional of t or a completable feature of t. And I think that eventually becomes very, very, very useful. So we're used to abstracting over, say, a list of A or some other type parameter. What we're not used to is abstracting over a T event, where T is a type parameter. So the thing on the left is the thing we're abstracting over. And that's often called a type constructor because it constructs a type. So you give it an int and then it becomes a real type. And of course you can actually abstract over both. So you can say, I don't care what's inside it and I don't care what it is, but somehow I'm going to write a function which is useful. Until you see lots of examples, I think you think, why on earth would I want to do this? But I think before Java 1.5, we got on just fine without the normal types of generics. So I'm going to talk about some motivation before I show how it works. So so far in the talk, I've represented a HTTP request as a function from HTTP request to HTTP response. A lot of async web frameworks, the newest version of Spring and Akka HTTP, which is one I work on, they actually represent it more like this, as a feature, which allows us not to block on database connections and HTTP clients and all sorts of things, which allows us to be more efficient and use fewer threads. Another thing which some people don't like is the use of exceptions. Who here likes exceptions? Who here thinks they'll like goto? Because I think they'll like goto. So a lot of people don't like them. And an alternative to them is either. Right? So either is a type which says I'm going to either return an error or a HTTP response. So you start to represent exceptional circumstances as values, as things like these either classes, rather than throwing exceptions. But that's another example of a type constructor. It just happens to take two types now rather than one. But before we go into why this is useful and why higher kinded types would be useful for this, we kind of have to fix our function composition. Because the whole point of making a HTTP request return a feature rather than a HTTP response is that we want to be able to do our database stuff and our calls out to external services stuff without blocking a thread, which is common in a lot of web frameworks now. Remember what our types look like. We had a serialize, which is from customer to HTTP response. We had a deserialize, which is HTTP request to person. And I don't think they involve any network or file systems. They might do, but in my example, they don't. So they can stay synchronous. They don't need a feature in them. They don't need an either. Apparently, we're not doing validation or anything. So they're going to stay as they are. But creating a customer, what happens if you need to make a call out to your company user registry to validate this is a real person or this customer hasn't already been created? This might involve something asynchronous. So we are going to have to represent create customers as a feature. We're definitely going to have to do the database one, because you can't talk to a database without going over the network. And if we try to do our function composition, it breaks, unfortunately. We get this far. We can still deserialize the person, we can still create the customer, but we end up with a function from HTTP request to feature of customer. And remember how function composition works is the next one has to take in the return value of the previous one. So we've got a feature of customer, but we have no functions which take in a feature of customer. The next thing that we'd want to do would be to save it, but it doesn't take in a feature of customer, so we need to fix that somehow. We're going to use two functions for that, which happen to be on the feature class inside Scala. We're going to use one called flatMap, and we're going to use one called map. What a flatMap does, if you haven't seen it, if you've worked with the completable feature inside Java 8, it is called then compose, and map is called then apply. These functions do exist on the optional class with these names inside Java. And all they allow us to do is take a feature of A, which in our case is, I don't remember, what do we have? We have a feature of customer. And we can pass in a function which takes the thing which is inside the feature and produces another feature. Which is really common, right? You call one service, you get a response back, and when you're done with that, you need to call another service. But you need the response from the previous one. And this kind of fixes our function composition, because that's what we have. We have a feature of customer, and then we have another feature, we have another function, which goes to the database, which goes from a customer, actually goes from a customer to a feature of customer. So we can use flatMap for that. Map is very similar, but you don't need to introduce something new. You don't need to have another asynchronous computation. We just transform it whenever it comes back. So we can use these two functions. We can use flatMap and map to fix things. We can do the first step, which is as far as we got before we broke our function composition by adding in the feature, and then we can flatMap and we can pass in save customer, and we get that we get a little bit further. We end up with a function from HTTP request to future of customer. Now the final stage was deserialization. That didn't involve any more futures, so we don't use flat map, we just use map. And then this will compile and this will be our new function composition. This is such a common pattern that certainly in the Scala ecosystem there are multiple libraries that do it for you. So I'm going to call it supercompose. You can take a feature from like A to feature of B and a feature of B to feature of C, and you can compose them. This is what you get, blue screen. Woohoo! Change resolution. We're okay. Anyway, this is such a common pattern when doing this style of programming that you can just use this function called supercompose. However, that supercompose is only written once in these libraries, and it's done by the fact that you can write functions in Scala that abstract over the fact it's a future. So you can use the same supercompose function. It's not really called supercompose. You can use the same supercompose function whether this was an option or an either or all sorts of different types. And this is a big topic, but there's a couple of links there if you want to go and read all about it. But rather than use supercompose, we're going to rewrite all of that code to work with eithers, because we decided we didn't want to be asynchronous because that was a fad, but we did want to stop using exceptions because that's our new fad. So we're going to redo the function composition with either rather than future. Well, not really. We're going to show you how you could write your code so that it would work whatever the f is, whatever that type is, whether it's future or completable future, and show how you can flip between using a completable future or a future or a either or an optional or all of these lots of types. And we're going to introduce some new funky syntax, which is a type parameter which takes a type parameter, also known as a type constructor. You see this, if you're used to Java, imagine that every square bracket is an angle bracket, and it starts to look a lot more familiar. This f with this extra little square back underscore thing is a syntax for saying, this is an abstract class, we've got this type parameter, this generic, as Java calls them, but it has to have one type parameter. So I couldn't instantiate this by writing new abstracted int or new abstracted string inside the angle on the square brackets in Scala, because string doesn't take a type parameter. But I could put future in there. I could put list, I could put completable future, I could put all sorts of different types. And then we just write the rest of our code, assuming that it's just f. We don't really care what name it is. But we do care a little bit, because when we redid our function composition using the futures, we used a couple of methods on them, on the future. We used flat map and we used map. So this syntax with the colon mapable basically says, actually I really do care about what it is. I care that it takes a type parameter, it's some kind of container like a list or a future, etc. But it also has to have a couple of functions. It has to have map and it has to have flat map. And then at that point, we can write our function composition in terms of this f, exactly the same code except we've removed uta. So now we're just f in there rather than future. And then we can decide later whether we use a future or something else. So we can write this code. This will compile, but it requires some machinery, which we'll look at in the implicit section. So if I were to abstract this, if I were to instantiate this with a feature, then the type would be HTTP request to future. If I were to instantiate this with an either, the type would be HTTP request to either. And that way, you don't care. You can implement your real code, not really caring whether we're using futures or all sorts. And if I was sitting there and thinking, is this useful? Why on earth would I want to write code where I don't know what the type I'm using is to represent the fact it's asynchronous? The last big Java project I worked on was, it had to be asynchronous because for scalability reasons, so we couldn't use a request to the thread. So you had to pick an async web framework in Java. We picked Ratpack. Right? Ratpack has its own asynchronous construct called a promise, and it has a flat map and a map. We used Hystrix extensively, so any external call out was wrapped in Hystrix, so we could have circuit breakers and all sorts of things. If you want to use Hystrix asynchronously, do you think it uses Ratpack's promise? No, it uses Rx Java's observable. We use Cassandra as the database. Cassandra is an async database. Do you think they use Ratpack's promises or Rx Java's observable? No, they use Guava's listenable future. That has a flat map, that has a map. It's a very similar type doing the same thing. And then we had lots of code internally which used Java 8 completable future. But without the ability to write code which abstracted over which one of these things we did, We didn't choose to use 4, we were forced to use 4 different ones by the other technology choices that we'd made. Most of that code base, from what I remember, was converting between these different async constructs. And it ended up kind of flipping in all over the code base. So I think this is kind of useful, but it is very unfamiliar when you first look at it. So the code I showed you before did have some things missing, and the reason this is possible inside Scala is you do need some implicits. Some other implicit features. So we've only got a few minutes left now, and I'm going to race over some of the features which I think are bad with implicits, and then finally one good one, which is how to make this mapable stuff actually work. And what I've found over years of using them is they do tend to replace runtime reflection, or something I used to previously use runtime reflection for. So I actually think implicits are more explicit than the thing I previously used. Real life example of a bad use of implicits. Converting between types that are concrete. So if I had a cat, and I do have 2 cats, and I have a dog, I don't have a dog, but I used to have a dog, and I write a function which cleans my dog. So I'm going to clean my dog, and this is a copy constructor where you just override one of the fields, and I clean it with a hose pipe to go for walks to get very dirty. Should I be allowed to clean my cat Ruby with this function in a statically typed programming language? I don't know. They don't have like a common parent, etc. If you think maybe it could be funny to clean my cat with a hose, it might be, but I think once you see her, you won't want to. Does anyone want to clean Ruby with a hose pipe? No? Anyway, Ruby is quite a nice-natured cat. She would forgive me if I cleaned her with her hose pipe and if she was implicitly converted into a dog. Her sister would not. She's a bit of a grumpy cat. I suggested to her that I turn her into a dog and clean her with a hose pipe, and she looked at me like this. Sister was fine about it, she just fell asleep. However, that is something we can do inside Scala if we use concrete implicit type conversion. We could write this bit of code if we also write this bit of code. Right? You can prefix a function with an implicit in Scala, and it allows the compiler to find bits of code that doesn't compile and try and shove the parameters into it to try and make it compile. This is terrible, I think. It is. It's very hard to discover what's going on. You remove an import and you think, why on earth doesn't this compile anymore? It's not a good idea. There are code limiters, there's certain ones we use which just disallow this and will give you a warning. IntelliJ actually, over the latest version, introduced a feature where any time an implicit conversion was used, it underscores it. So now it's reasonably discoverable in IntelliJ now. However, converting between concrete types, I think, is a really bad thing, and it's one of the main reasons that implicits have got a bad name in Scala. But converting to types that are only designed to be converted to by implicits, which I've dubbed principal type conversions, is a feature which enables our previous thing. So we had this trait mapable, which represented what our type constructor, like feature or list, requires to be used inside our business logic. And we decided we needed map and flat map. So for the previous code to compile, we would also need to do this. And it shows the Scala compiler how, for a future, we would implement map and flat map. And it's really easy because feature has a map and a flat map, so we just delegate it to it. But imagine you really fell out with the Scala feature. You decide, no, we don't like it. We don't like the guy who wrote it. He wears silly caps. We wanted to move over to the completable feature from Scala. Sorry, from Java. Then we would have to provide a different implicit. And it's cut off a bit, but it says completable feature at the end. It doesn't have a map and a flat map, but it has 2 functions which do exactly the same thing. So then the previous code would compile with a completable feature instead. Right, we're definitely coming to the end of my time, so I will summarize by putting the same bullet points up again and not describing them. I was going to quickly run through what I think it takes to have a successful Scala project. I think the top one is the most important. Scala is a new programming language. It is not Java. It is not Kotlin. Whereas Kotlin is semantically very similar to Java, Scala is not. It's very different. So because we're out of time, I'll say thanks for listening and just come grab me after if you've got any questions. Cheers.